This presentation expands on the VMware vSphere 5 Memory Management and Monitoring Diagram in Knowledge Base Article 2017642. When you're viewing the Resource Allocation tab in vSphere 5, you have a dynamically updated view of the current memory usage for a virtual machine or resource pool. The top section under Host Memory is the physical memory in use, with the second bar being how much of the used memory is memory overhead. That is the physical memory used to run the virtual machine. Some of the factors that affect the memory overhead consumption are number of virtual CPUs, amount of virtual memory, number of virtual devices, and the capabilities of the physical processor. This table provides a sample of overhead memory values on virtual machines. The next section is the guest memory. The fields are as follows: private, physical memory on the chip; shared, memory that is provided by transparent page sharing; swapped, memory that has been host swapped. If this number is high, it may result in performance issues; compressed, memory that has been zipped. Compression provides better performance than swapping. Ballooned, memory reclaimed from the guest by the ballooning driver. Unaccessed, memory that is untouched by the virtual machine. And active, approximate amount of memory being actively used by the virtual machine, the reads and writes. ESXTOP is a valuable tool for troubleshooting performance issues. Typically, it is best used when you already know you have a problem. Here is a sample screenshot of an ESXTOP set up for a general overview of memory management. See the resource management documentation for more information on customizing this view. These values are the physical memory and VM kernel in megabytes. The physical memory is the total physical memory available, while the VM kernel memory shows how much of that memory is used by virtualization. This is the state or status of the memory. There are 4 possible values for the state: high, soft, hard, and low. The high state is the most preferred state to be in, and as you work down into the low state, memory overcommitment solutions are implemented more aggressively. P-share is how much memory is used for transparent page sharing. This number shows how much memory is being reclaimed by TPS. These numbers show the swapping activity of the VM kernel, also seen here in the columns for each virtual machine. Related to host swapping is the cache swapping fields, similar to host swapping but using the cache as storage. The size target column is determined by reservation, limit, and memory shares. This column is a Boolean field displaying yes or no if the balloon driver has been enabled for that virtual machine. The next columns are the current size of the balloon section memory, the end target of the balloon section, and the maximum size the balloon section can be, established by the host. The final column shown here is the VM memory overhead. This lets you know per virtual machine how much memory is in use running the machine. Transparent page sharing is when pages of memory that are identical take up the same physical space on the physical memory card. TPS can occur within a single virtual machine or across multiple virtual machines. In this diagram, there are 3 virtual machines on one ESX or ESXi host. Each virtual machine has its own logical and physical pages. At the bottom is the physical memory module. Without TPS, the physical pages of the VMs would take up a majority of the space available on the card. With TPS, it looks at the page contents of each page of data and checks to the other pages of data existing, reclaiming pages that have identical data, allowing for more available memory. The memory balloon driver collaborates with the host to reclaim pages that are considered least valuable by the guest operating system. The driver uses a proprietary ballooning technique that provides predictable performance that closely matches the behavior of a native system under similar memory constraints. This technique increases or decreases memory pressure on the guest operating system, causing the guest to use its own native memory management algorithms. When memory is tight, the guest operating system determines which pages to reclaim, and if necessary, swaps them to its own virtual disk. Host swapping can have a heavy performance impact and is used as a last resort for reclaiming pages. The host driver swaps lower priority pages onto the physical disk where it can still be accessed. However, memory backed by a physical disk has significantly higher latency than physical memory. Once memory is being swapped, pages that can be identified with a minimum 50% compression ratio may be compressed and kept in physical memory. The host zips lower priority pages so that 2 or more pages can occupy a single page of memory on the physical memory module. Compressed memory has small overhead on reading memory, however writes to the compressed memory slow down processing. For more information, see the following guide. Thank you for choosing VMware. By clicking on the annotations below, you can follow the Support Insider blog for updates and alerts from the VMware support team, view more videos on VMware and VMware products at the KB2017642 channel on YouTube, or follow us on Facebook and Twitter for the latest updates, alerts, and VMware support.